Hello and welcome to today's IWCS webinar. My name is Connie and I'll be your WebEx producer for today's event. Now I'm pleased to turn the webinar over to Ed Fenton, your IWCS moderator. Ed, please go ahead.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact a presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly, and they will respond individually to you. Today, we welcome Jim Register, Development Associate, Corning Optical Communications in North Carolina, USA, who will be presenting his paper on development of a low contraction jacket material and drop cable applications. Jim Register is a Development Associate for Corning Optical Communications. His experience includes the development of drop, composite, flame retardant, and specialty optical fiber cables. He graduated from North Carolina State University with a BS in Mechanical Engineering in 1992 and has been employed at Secor Corning for 27 years. He has previous experience in field and applications engineering prior to joining Corning RD&E. Jim, we welcome you to present at today's IWCS webinar series event.
Thank you, Ed, and I'd like to thank Connie and Dave also and the IWCS for allowing me this opportunity to present and for running such a well-done professional seminar series. So good morning, everybody. This presentation will demonstrate a flexible drop cable solution that functions at a small bend radius in the outside plant. And the key factor here is that this cable will have no dedicated anti-buckling elements. The solution is enabled by a new low contraction jacket material, and I'll talk more about that. While this cable solution is primarily targeted at a specific cable design, and the one I'll talk about today is for the European cabling market, the functionality of the new jacket is applicable across many conceivable scenarios. The FTTH, fiber to the home market for homes passed and subscribers in Europe, is expected to grow significantly, and I'm showing here data through 2025. This growth is being driven by regulatory incentives, funding to promote fiber to the home, and 5G deployments. And, you know, in the last few months, we also have the obvious need for more bandwidth due to COVID activity. Growth of video content is also forcing higher bandwidth and lower latency needs. And municipalities are also expanding networks in less economically viable areas. This chart shows expected homes passed through 2020 for the 28 European countries, as well as a group of adjacent countries represented here by EU 39. This growth is still expected to double through 2025. The second chart shows the number of subscribers, which are expected to grow even faster, due to the lag between homes passed and subscriber take rates, which are still below 50%. This will enable substantial growth in this drop cable market for the foreseeable future. This market introduces multiple installation challenges due to constrained installations such as facades, small handholds, and this points to a need for a small, flexible, and round drop cable solution. These cables would also benefit from small, easy-to-install clamps Flat drop cables are used extensively in the outside plant. However, applications exist where a round drop cable is also desirable. The flat drop cable is very robust, characterized by the use of parallel, rigid strength elements. These rigid strength elements create a design that is suitable for self-supporting applications, work well at low temperature environments, mainly due to their low contraction quality. However, the bend radius is negatively impacted. Some scenarios, such as small flower pot type handholds, still need to be robust in the outside plant. The round drop cable can work in the tight outside plant applications, plus be broken out into a flame retardant inner unit that can be installed indoors. So the Corning's round drop cable solution is designed for underground and aerial fiber to the home applications with an outside layer of UV protected polyethylene jacket. There are hard fiberglass yarns used to provide anti-buckling strength, particularly during cold temperature cable contraction from 0 degrees Celsius down to minus 40 degrees Celsius. The cable has a dual function aspect in that separately routable inner unit is designed for indoor routing and functionality. As I will show later, the use of stiff fiberglass yarns for anti-buckling can induce attenuation for very tight bend radii, depending on how the yarns are processed. And we'll talk about how we solve those problems. Okay. The key driver for cold temperature performance is the coefficient of thermal expansion for the composite structure. This can strongly influence by the jacket materials. The video shows contraction of a simple arrangement of a buffer tube containing optical fiber stranded around a rigid GRP. Here, the jacket and buffering components tend to shrink at greater rates than the optical fiber. This can be mitigated using anti-buckling components. In this video, the GRP serves that purpose. In the cable that we're talking about, the stiff fiberglass yarns are taking on that function. Therefore, general cable design thus becomes a balancing act of mitigation, relatively high coefficient of thermal expansion materials with low coefficient of thermal expansion anti-buckling components such as GRPs. For the round drop cable shown earlier, the impact of longer fiberglass yarn lay lengths on bending attenuation has been quantified. And you can look at the chart on the upper right corner. This chart shows drop cable bend diameter where the onset of attenuation is observed. The horizontal axis shows lay length, and the vertical axis shows bend diameter. The red line shows the customer spec that drove this work. Connie, I'm not getting my page down. It's not working anymore.
Did you click on the slide again?
Okay. Thank you. The green area shows to meet customer bend radius specification, highlighted in green, the yarn lay lengths need to be as low as 100 millimeters to limit the induced attenuation. This happens because at longer lay lengths, the hard fiberglass yarns stretch and buckle during the bending operation. This induces macro bending on the fiber through the subunits, inner yarns, and the tight buffer layer. So in order to make the cable functional for the application, a short lay length is required for stranding the yarns. This is a problem because of productivity of manufacturing, since it requires lower operational line speeds. The line speed limit is driven by the physical size of the yarn packages, and since you may only spin the yarn packages so fast before you see a loss of stability in the yarn package. So you essentially have a limitation on line speed. One way to solve this problem and the method that we employed here for this presentation is that we are introducing a low contraction jacket material. A basic model for thermal strain is that the length change is a function of component expansion coefficients, component areas, and component modulus of all the materials. By sufficiently reducing the thermal strain, a reduction in attenuation or expanded operating temperatures, or a reduction in anti-buckling components can be achieved. In order to create the low CTE jacket, three major components were used: a standard polyethylene base, a styrene, ethylene, butylene styrene, or SEBS, thermoplastic elastomeric material, and a nanoclay filler were used. The key functionality for lowering this CTE is obtained by orientation of the filler and the MDP in a co-continuous elongated structure where it acts as a laminate structure. The third graphic shows how the CTE is affected by this laminate structure. The center photo shows morphology of the co-continuous structure. This photo was obtained by using a solvent to remove the elastomer, leaving behind the polyethylene material shown in gray. The last photo shows a structure where the orientation and the co-continuous structure is less defined. Here, the CTE measured using thermomechanical analysis shows an increase of greater than 40%. The result is that the CTE is significantly reduced for the non-co-continuous structure. Since this modulus also decreases, you get a reduction in CTE from the morphology change as well as the modulus reduction. The resultant improvement is that the new low contraction jacket has approximately 40% lower CTE, 15% lower modulus, 65% lower contraction force compared to an MDP jacket material. This reduction in modulus is not significant, and the yield stress change does not exhibit any mechanical performance issues. The new material processes very similarly to normal polyethylenes. There's been no need to change temperature profiles or extruder pressures are not significantly affected. The shrink back, however, has shown no significant change and needs to be accounted for in cable design. So in order to demonstrate the effectiveness of the low contraction jacket material, a precision test bench was used to measure length change of a composite structure. Our first run was using a 1.6 millimeter GRP overcoated with MDP to 2.7 millimeters. And length change was measured versus temperature change. And the blue bars show the length change basically from -40 to +70. The new low contraction jacket material is compared in the yellow curve, and by shifting that in comparison to the MDP curve, you can see that the length change of the composite structure is shown to be approximately 20% less than the straight-up MDP overcoated GRP. So this experiment showed promising demonstration of the jacket material. The new jacket was then, the next thing we need to do though is verify temperature performance in an actual cable. So the new jacket was then compared against a medium density polyethylene jacket on the round drop cable using soft aramid yarns in thermal cycling. Okay, so we're basically getting rid of the anti-buckling elements as described earlier in the potential benefits for the low contraction jacket. For this testing, both cables were run with parallel application. The first chart shows cable attenuation performance of the MDP jacket over 6 days of thermal cycling in the environmental chamber. And the y-axis shows basically on the right-hand side, the black curve shows the temperature profile. The red data points on the left-hand y-axis that shows attenuation response at 1550 nanometers in dB per kilometer. And the time period in days is shown on the x-axis. The MDP cable, as you can see, had pretty poor performance with maximum attenuation on the order of 25 dB per kilometer. Looking at the new low contraction jacket, you'll note first that the scale of the attenuation response has changed so that you can visualize what's going on. The cable with the low CTE jacket showed a maximum of 0.06 dB per kilometer across 6 days of thermal cycling, and this is obviously a significant improvement. So the next thing we needed to do was validate how does the new jacket material perform in the bending test, because ultimately that was one of the things where we were having problems with the customer specification. So the first, we looked at different jacket yarn combinations, and the first shows using a bend diameter of 60 millimeters with 5 180-degree bends, attenuations evaluated using the base cable design, okay? And as you can see, and this was framing up as a control, what we were originally up against. If you lower the lay length down to 100 millimeters, you get good attenuation response in bending. If you go to a longer lay length, you have problems. The problem with running a 100 millimeter lay length is line speed, which reduces productivity. Using parallel aramid for both the MDP and the low CTE jacket, there still exists a bend attenuation issue. So neither one works in this case. When using parallel aramid, both the MDP and the low CTE jacket passed the bending test. Therefore, the takeaway from this slide is that the straight aramid works for the bending test, but if you recall the previous slide, you have to have the low CTE jacket for the thermal cycling test. So it's a combination of yarn coupled with the new jacket material to pass this test. This chart is a summary, and in conclusion, it summarizes bend performance for the round drop cable design. It shows the yarn lay length and associated line speed on the y-axis and limiting mandrel diameter where no attenuation is seen in the 5-turn mandrel bend test. The green highlight shows that a soft straight aramid coupled with low contraction jacket meets the customer specification for bending performance and also the internal need for processing at high line speed. The stiff yarn high CTE jacket, both the yellow and the red highlighted areas shows that only the low line speed condition in red meets the needed customer mandrel diameter. So in conclusion, the new low contraction jacket reduces the need for anti-buckling components in the outside plant cable. The cable with the low thermal strain design enables a parallel aramid solution that runs at higher line speed and functions at small bend diameters. So Thank you, everybody, and I'd like to pass it back to Ed and Connie.
Thank you, Jim. And at this time, we will ask as many questions from the attendees as time permits, starting with this first question. Are there any unique drop cable installation techniques or other requirements to be considered in different regions of the world? Would these require different materials or cable designs?
Ed, could I get you to repeat that? I kind of missed the first part.
No problem. Are there any unique drop cable installation techniques or other requirements to be considered in different regions of the world? Would these require different materials or cable designs?
Yes, and that's a good question. As noted at the beginning of the presentation, we're going into a lot more dense type of environments, especially with duct flower pots and the like, where your drop cables aren't the typical self-supporting type to the house, but it's more of a dense architecture. So the key here is that, yes, bin radius becomes a factor because of the density concerns, and in order to manage cold temperature conditions, we need different jacket solutions to enable that. So I think that is basically a confirmation of the basis for this cable design.
Okay, thank you. Next, would the same comparisons between flat and round drop cables apply if using PVC compounds rather than olefinic or LSDH components?
Yes, it would. And with the PVC material, the difference would be, and you know that putting a PVC compound over a flat drop design, for example, potentially impacts flame requirements for that. But you still have the bin radius concerns that you have to address, and you know, a lot of jurisdictions like Europe, for example, don't use PVC solutions because of the non-olefinic nature of that and the halogens involved. So I think you would have to consider them the same way we're doing here.
Okay, thank you. Next, does the softness of yarns impact the required properties of the low contraction jacket material to limit the thermal strain, or is the jacket material independent of the internal cable components?
In this case, the jacket material is independent of the internal cable components. The interaction of the yarns, for example, is basically an interaction between if you remember the dual drop, and I'll go back to that slide. If you remember the dual drop nature, basically the bending performance was dictated by the impact of the yarns, stiffness of the yarns on this internal component. The only time that the jacket and the yarn configuration could potentially be a factor in this case if you have a bonding mechanism between the yarns and the outer jacket, and we haven't observed that.
Okay, thank you. Next, if the jacket contains flame retardants, do these ingredients affect the coefficient of thermal expansion properties?
Yes, they obviously would. And for this material, we currently, you know, one of the desires for this cable design is basically to make it in a, and this cable design is obviously designed to have the internal unit structure that can be branched out for flame retardant applications. If we did add flame retardants, yes, it would impact that, but the current material is not designed for flame retardant, but really for outside plant performance.
Thank you. Next. Dispersion of nanofillers in polymer is one of the difficult processes. How do you achieve exfoliation dispersion with nanofillers?
I will have to take that question offline. As you remember, I've been working with a material scientist on this, and he's probably more in tune with the actual processing of the jacket compound.
Okay. In a follow-up, maybe the same response, but I'm going to ask, what kind of nanofillers are best suitable to get low CTE?
I am going to defer that question too.
Okay, thank you. Next, what do you suggest to spin the aramid or use straight specifically in round cables?
There's lots of equipment on the market for doing that. I'm going to defer on that question.
Okay, thank you. Next question. Does the new cable reduce the bending loss as well?
Yes, that's the whole premise behind it. At low bend diameters, we were having attenuation issues. So, yes, that is one of the mechanisms.
Okay. Next question. Did you consider other soft reinforcing fiber options such as LCP or HMPE?
Not for, and there's other ways that we could have potentially solved this problem, and we chose this route, and we think that a low contraction jacket, not only for this design, but potentially other outside plant solutions, offers inherent value. So we didn't go that route. Obviously, there might be alternative ways to skin this cat, but we chose the low contraction jacket.
Okay, great. Next question. Have you considered other geometries of GRP to combat the anti-buckling, such as flat GRP? It's a proven solution to combat this condition?
I am going to, no, we haven't looked at that specifically.
Okay. Next, how much post-extrusion shrinkage may affect, as we have noticed that once the drop cable was made, the attenuations are fine, while after 1 day or two, we found events in the lower bottom while on the drums?
Yeah, so, and I kind of alluded to that fact. You know, the shrinkage is still relatively similar to a normal olefinic compound, and that is, our cable design basically has to account for that exactly as you noted. How does storage environments affect the optical attenuation? How do the operating conditions, and there's lots of factors involved in that. You know, excess fiber length is just one, lay length of the components, and the whole overall structure of the cable. So that's one of the things that we just have to manage just by normal cable design techniques.
Thank you. Next question. What is the ballpark figure overall diameter for this cable?
Oh. Let's see. I'm going to have to go offline. We've got an exact diameter, and I don't remember what it is. I'll have to get back on that.
Okay. At this point, Jim, I'm seeing no further questions. So I would like to thank you for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Jim after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, July 17th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so they can join in and register as well. For over 68 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next 69th Annual International Conference will now take place virtually in October of 2020. Please watch your inbox, social media, and our website as this exciting information becomes available. Also, the next UL and IWCS China Cable and Connectivity Symposium will take place on Tuesday, March 23rd through Thursday, March 25th, 2021 at the Marriott Hotel City Center in Shanghai, China. Please visit our IWCS.org website for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.